Hello friends, welcome to NPTEL online certification course on soil and water conservation engineering. I am Rajendra Singh, professor in agriculture and food engineering department of IIT Kharagpur. We are in week number 3, lecture 14, and topic today is graded bunds. Just to remind you of the course content of week 3, in this week we started lecture 11 with introducing bunds. In lecture 12, we went through the concepts of contour bunds. In lecture 13, we saw how to apply those concepts for designing contour bunds. In today's lecture, we will go through concepts of graded bunds, and then in lecture 15, we will see how to solve problems on graded bunds or how to design graded bunds. Just a recap, this we already saw earlier that graded bunds are small embankments that are laid across the land slope, but not along contours in agricultural fields. So, basically small embankments, just we saw already that be it contour bunds or graded bunds, they are typically small embankments, and also the cross section is typically trapezoidal. And they are always like we have already seen that all the conservation measures we adopt, they are always taken across the land slope, because we want to check the flow of water, that is the basic purpose. And important point here is it and not along contour. This is to distinguish that graded bunds are different than contour bunds. In case of contour bunds, we always put the bunds on contour lines, where in graded bunds we do not have to follow the contour bunds. This is the major difference. In these bunds, that is graded bunds, the entire spacing between two consecutive bunds acts as a channel, where a longitudinal slope along the bund is provided for letting the runoff out safely from the channel. So, basically what it says is that if this is your land slope and suppose we are adopting these graded bunds, two consecutive bunds. So, that simply means that what it is saying that in the case of contour bund, we saw that whatever rainfall occurs in between these two bunds, that we try to store that we try to conserve over the total area. But in this case, what we also saw that the function of this is basically disposal of excess water, safe disposal of excess water. So, that is why this entire area here, and when we say area, there is a length perpendicular to the board also, that is very important. You have to understand that this is there is this, if we can draw like this in this direction. So, this is something like this, in this direction this will continue along the length of the field. So, this we are talking about is this is the horizontal interval and this is the length. So, this along this length there is a longitudinal slope, we provide a longitudinal slope, and this entire thing, the area between these two bunds, that acts as a channel. So, that this entire area acts as a channel, and then we provide a longitudinal slope along the bund for taking the runoff water away through some safe disposal. So, basically that is where this longitudinal slope along the bund is coming into picture, and obviously then the entire channel is used for letting the runoff out safely from the channel, that is the purpose. These are preferred in areas where land is susceptible to water erosion, soil is less permeable, and the area has water logging problems. So, wherever of course, susceptible to water erosion, that is why we are going for any erosion control measure, be it contour or graded bund, but in this case the qualifying statements are that soil is less permeable, that means the infiltration rate is very low or infiltration capacity is very low, and the area has water logging problem, that is water gets stored because infiltration capacity is low. So, wherever these conditions are there, we go and adopt graded bunds. And just to remind, the graded bund system is primarily designed to dispose excess runoff safely from agricultural lands. So, any area which is waterlogged or where the soil is less permeable, obviously we do not want water to get stored there, and that is where we adopt graded bunds, so that the excess runoff can be safely disposed of. So, the major difference between the contour bund and graded bund is that the contour bunds are constructed for water conservation. So, they are water conservation measures, where graded bunds are meant for disposal of excess runoff. So, that is one major difference between contour bunds and graded bunds. And in the case of contour bund, the area between two bunds, that is used for conserving moisture, where in the case of graded bund, the area between two is used as a channel for safely discharging the water or carrying the water to a safe outlet. That is the major difference between these two bunds, types of bunds. Now, typically adaptability is concerned, these are constructed in high rainfall areas having more than 700 millimeters of rainfall, and where the excess water has to be removed safely to avoid water stagnation. So, basically in high rainfall areas having more than 700 millimeters of rainfall, this is a typical adaptability condition and usually recommended for 2 to 8% of land slope. So, we saw that 2 to 8% of land slope is or less than 8% is recommended for both contour and graded bunds, and general recommendation for contour bunds is 2 to 6%, here it is 2 to 8%. Contour bunds are for usually adopted in less than 700 mm of rainfall, whereas graded bunds are adopted for more than 700 mm of rainfall under normal circumstances. In case of highly impermeable soils like deep black soil, graded bunds may also be recommended for lesser rainfall areas. So, if they have to be adopted in less than 700 mm of rainfall, then the conditions has to be very specific, that the soil has to be highly impermeable or its infiltration capacity has to be very low. For example, like it happens with the deep black soil, and that is why if you go to Bellary region of Karnataka in southern state of Karnataka, then you will find that typically because the soils are deep black soils there. So, graded bunds are preferred in those areas. Then we have already seen that we provide some kind of a longitudinal slope here. So, this is the channel. So, we provide some kind of longitudinal slope depending upon which direction we have to take the water, and this gradient may be uniform or variable, that is also a possibility. You can have a uniform throughout the length, or the grade could vary also. The uniformly graded bunds are suitable where the discharge is less, and thus the length of bund is also less. So, if the bund of discharge to be handled is less and the length of the bund or the length of the field itself is less, then we go for uniformly graded bunds. And variable graded bunds are suitable where the discharge is more and length of bund required to handle the discharge is more. So, on the contrary, if the discharge is more and the length of bund is more, then we provide variable grades, and variable grades are provided in different sections of the bund, so that velocity of flow is kept within non-erosive limit. So, be it the case of uniformly graded or variable graded, this condition of non-erosive velocity is always true. That is, you always have to see that water flows only at a non-erosive velocity, so that there is no erosion in the channel. And but in the case of variable grade, if it is the length of the bund is more, we can provide variable grades in different sections of the bund. So, water flow in the graded channels constructed on upstream side of bunds is at non-erosive velocities, and the flow is led to safe outlets or grassed waterways. Sometimes, I mean, though we have said that the entire area between the two bunds can be used as a channel, but sometimes if the discharge is not so much or it is not expected to be very high, then we also provide that just construct channels upstream side of the bund. So, that simply means what? That just now we saw that if this is our example, once again I draw this. Two consecutive bunds, And again, to make it easy to understand, let us say that we are putting a third dimension also. So, that means this is the land slope, across this is across we are constructing these bunds, and this is the area we are talking about. So, in the previous case we saw that while defining the graded bund, we said that entire channel area is used as a channel. I mean, entire area between these two bunds is used as channel, but in some cases like the case it is saying here that graded channels constructed on the upstream side of the bund. So, if this is the upstream side of the bund, in this case it will be here, because the slope is in this direction, we are saying slope is in this direction. So, water will flow. So, that simply means by the side of this bund itself we construct this channel. Just channel is constructed here and the grade is provided there, and the remainder of area is left as it is. So, that is also a possibility. But in any case, the channel portion of the graded bund is put under cultivation, and the grassed waterways are kept permanently under grass. So, depending upon we always cultivate the bund areas, which is why we really go for this conservation measure, but the grassed waterway or waterway wherever we are carrying the water through, that should be kept under grass, so that erosion can be checked. That is very important. Now, coming to design of graded bunds, there are certain aspects we have to keep into account. So, like in the case of contour bund, we need information on rainfall, which gives us an idea about how much water really the structure is likely to handle. The land slope, which basically first thing is it decides, it helps us in deciding the adaptability, which kind of bund, or also this land slope is used in designing various other parameters of the structure. Then soil texture and soil depth. So, these are the three basic information which we require, and based on the soil type we select a suitable side slope, and subsequently calculate the vertical and horizontal intervals and determine the bund cross section and grade. And bund cross section, when we say, it includes base width, top width and bund width. So, these are kind of repetition for what we have already seen in case of contour bund. The bund design also includes estimation of length per hectare of the land, which helps in estimating the total earthwork and cost of constructing the graded bunds. The design of any graded bunding system is based on the value of estimated design discharge from the field, which is quite obvious, and the known value of design discharge and other location specific variables like soil type, rainfall, infiltration are related mathematically to determine the different design parameters. So, that we will see one after the other. Now, coming to definition sketch, that is various design parameters, very similar to the graded bund, contour bund, but here also once again we see this is the trapezoidal cross section normally we use. This is the trapezoidal cross section here you can see, and the bottom width is B, top width is T, and H is the total height of the bund, and H is the depth of water pounded behind the bund, or theoretical depth, which we normally calculate first, and then we provide the here basically the difference between H and H is nothing but we provide a kind of freeboard. So, this H is calculate, and then we add freeboard to get the total height, and Z here is the side slope. We always said that we always represent in terms of horizontal is to vertical, that is 2 horizontal is to 1 vertical. So, this value is Z is nothing but this side slope we have to put, and the NS is the slope of the seepage line, because this seepage line also has a particular slope, and that is being represented here by N suffix S. So, these are the various components we have to keep an eye on. Now, vertical interval, determining the vertical interval and horizontal spacing. the same principle which we used while designing contour bunds is adopted, and this is the vertical interval, this is the horizontal interval. We remember we had 3 different formulas, as I said that the Cox formula is most commonly used for calculating the vertical interval, where it is given as 0.3 x s plus y. X s is the land slope, y v is the vertical interval, and x and y they are the factors accounting for rainfall. This x accounts for rainfall of the location, and y accounts for the soil characteristics and also the crop cover conditions. And the values of x and y we always obtain from tables which we have seen in lecture number 12 and 13. Both those lectures we have used these tables to find the values of x and y. Now, grade, as far as grade is concerned, an uniform grade is used for short bunds of 100 to 150 meters, and variable grade when the bund length goes beyond 150 meters. For most of the soils, the grade ranges over 0.2% to 0.4%, but in case of long bunds with impermeable soils, the grade may be 0% in the beginning, that is the variable grade we are talking about, and may be increased to a maximum of 0.5% at the tail end. So, general recommendation is 0.2 to 0.4%, but if for a longer bund it could start from 0% in the beginning and it could go as high as 0.5% in the tail end. The side slope recommendations remain the same because they are function of soil characteristics, and so they do not change the type of bund. So, here the side slope is 1:1, and the side slope we are talking about is this side slope. So, 1:1. So, if it is a clay soil, this is 1:1. If it is loam soil, it is 1.5:1. Horizontal is to vertical, remember H is to V, and sandy soil 2:1. So, you remember these things we always used. Now, the most important thing, that is the height of the bund. The height of the bund, general recommendation is it could vary between 50 to 80 centimeters. That is the general recommendation. That could be 50 centimeter to 80 centimeters. But the calculation of the height of bund we can do, and there is a research paper published by Singhs and others in 2010, and so we will use that paper to express the same thing. And this is the cross sectional view of a graded bund showing design parameters. Most of the design parameters already we have seen, and some of these will be requiring and will be using slowly. So, here what is we are seeing that h is the height of the bund which is being used, and d is this triangle. There are 2 triangles which are used here. The 2 triangles being used here are ABC and BCD, and Z, generally we use Z as Z is to 1 slope. So, that is why if this is H, so this becomes ZH. Similarly, this is S% slope or S by 100. So, that is why for H it will be H 100 by S or S by 100 H by S. So, this length will be 100 H by S because the soil this is S% slope. So, with these definitions, let us see the total cross sectional area of the channel bed will be sum of areas of ABC and BCD. So, this is one triangle, this is the other triangle, there are 2 triangles, this is one triangle, this is second triangle. So, these 2 triangles area will be there. So, area of ABC, that is this is ABC, or this area is A1 is half into the vertical, that is H, and the base which is 100 H by S. So, that is being used simple triangular formula, area of the triangle formula we are using here, which comes out to be 50 H square by S. Now, for this one, this is A2. So, A2 is half into H times this, which is ZH. So, half into ZH times H or ZH square by 2. So, these are the 2 areas. So, total area will be obviously the sum of these two. So, the total area is sum of these two, that is 50 h square plus s plus z h square by 2, or h square taking common 50 by s plus z by 2. So, this is the area in terms of h and s. And discharge typically is given by the continuity equation q equals to a v, and where velocity is calculated using Manning's equation, which is given by v equals to 1 by n r to the power 2 by 3 s to the power half, where r is the r which is here is the hydraulic radius as given by a by p, where a is the cross sectional area and p is the weighted perimeter. So, we have to, if you have to apply this equation v, then we have to calculate the weighted perimeter, and weighted perimeter basically is if you read the channel, any channel. So, if it is a channel where this is the water level and we have to find out the weighted perimeters. So, all the surfaces, the sum of the length of surfaces which are in contact with water, this is referred to as weighted perimeter. So, this is weighted perimeter. Same using same principle here, the water contact is here and on this surface, and that is why the weighted perimeter is this length, which is P 1, and this length, which is P 2. And from the triangle formula, Pythagoras theorem, P 1 will be nothing but P 1 square is h square plus z square h square, or P 1 is square root of h square plus P 1 is h square plus z h square. This is one. Similarly, here P 2 will be square root of h square plus 100 h by s square. So, here. So, total P, that total weighted perimeter P will be sum of these two. So, here h taking h common, this is what we get. So, this is how we get the weighted perimeter. So, now we know the area, we know the weighted perimeter. So, we can calculate the hydraulic radius. The hydraulic radius is r equals to a by p. So, a r equals to a by weighted perimeter. So, a we have calculated, weighted perimeter we have calculated. So, that is how we get the value of r in these terms, in terms of z, h and s basically. So, now we can put everything into the velocity r equation velocity, and then substitute the value in q equation. So, basically what we are saying is that q equals to a times v and a times 1 by n r to the power 2 by 3 s to the power half. So, this is here. So, if we can put in this equation, remember there are two slopes being used here. This small s is bed slope, that is all the time we are using this in all equations, whereas this s which is coming is this one is land slope and this one is channel bed slope. So, there are two slopes, one is being designated by small s, one by capital S. So, let us not get confused, small s is land slope, capital S is channel bed slope. So, we have to remember this in this formula. So, basically we are simply putting the values of area and r which calculated, s already is there in continuity equation. So, after arranging these terms, finally, for h we will get this equation. We are simply simplifying the terms, that is h equals to q times n to the power 3 by 8 square root of 1 plus z square plus square root of 1 plus 100 s by square, the whole power is 1.4, s by 100 to the power 3 by 16 and 50 s by z by 2 to the power 5 by 8, where q is the discharge, z is the side slope, s is the land slope, capital S is the channel bed slope and n is the Manning's roughness coefficient. So, this is how using this formula we can calculate the h, and then gross height or the height of the bund can be determined by adding a nominal 20% or 25% freeboard. So, h will be 1.2 or 1.25 h, whatever we want to calculate, that is how it will come like. So, now we reach once we have calculated h, then we can go and calculate other things like cross section. So, there are some general considerations while designing the cross section. Cross section of the bund should be sufficient for stability, which goes without saying. So, the structure has to always be stable, and that we have to keep into account. The highest flood level should be below the top of the bund, and that is why we always provide the freeboard, because we do not want that. That is why we always calculate the theoretical height, and we calculate the we add the freeboard, so that overtopping is avoided. And the third consideration is the seepage line should lie below the toe of the bund on the downstream side. And seepage line is basically what happens, that because the material of construction is soil. So, obviously, whenever standing water is there, seepage starts taking place, and slowly this whole things gets wet. The problem is that we want to avoid this. We do not want that this downstream side should be wet, because the moment it happens, there might be failure of the structure, because the toe will fail. So, there will be cutting of the toe, and then the entire structure will fail. So, that is why we should always ensure that seepage lines should lie below the toe of the bund of the downstream side. And that is why when we take this seepage line, we always ensure that the seepage line crosses the toe, and or we can always say that seepage line must pass through the base of the structure. So, that is what we always recommend. Now, coming to cross section, the seepage line should have the following slope under different soil types. So, for clay soil it is 3:1, for sandy loam soil 5:1, for sandy soil it is 6:1. So, these are the general recommendations. So, while calculating the base width, we must take into account the seepage line slope recommended for different soils. So, we know that what is the soil material of construction. So, based on that, we should always take that into account. Now, the base width, when we calculate, obviously we have to take this into account. So, base width when we say, so base width will be having two components basically. If this is the h, so this one is to account for this slope, that is the z, the side slope of the bund itself, and this one to account for the slope of the seepage line. So, this slope is n s, this slope is z, and the height is h. So, obviously, this is z h, and this one will be n s times h, and that is why the total base width B is n s times h plus z times h, where n s is the slope of the seepage line and z is the side slope. Now, once the base width is calculated, the top width, which generally varies between 30 centimeters to 90 centimeters depending upon the height of the bund, generally it is 50 centimeters. Remember, in case of contour bund also, we say that for Indian conditions the top width is 0.5 meters and bottom width is 2 meters. So, just general recommendation. So, top width calculation obviously will take into account the total height of the bund which we have calculated, and so here T top width T will be base width minus 2 times 2 triangles have to be deducted. This is the one triangle, this and this is second triangle. So, this slope is z, we know. So, and this is capital H. So, this is capital H, and this is also z times capital H. So, B is, this is B. So, this is T. So, T equals to B minus 2h, 2zh. So, that is how top width can be calculated, where B is the base width, z is the side slope, and h is the gross height of the bund. And then comes the earthwork computation, like contour bund. Here also earthwork is the product of cross sectional area and the total length of the bund, and the earthwork that is earthwork equals to AC times L, or EW by L, we can say the area of cross section, and area of cross section we know always, it is a trapezoidal section. So, this is B, this is T, this is H, this is B, this is T, and this is H. So, area of cross section of a trapezoid is half times sum of T plus B times H. So, that is same here, T plus B by 2 into H, that is the earthwork, volume of earthwork in cubic meters, and L is the length of the bund in meters. So, this is per hectare basically we are calculating. So, this is how it can be, where L is the length of the bund in meters. And say then the cost of construction per unit length of the graded bund can be obtained by multiplying the earthwork volume involved in construction of unit length of bund and unit cost of earthwork. So, if we know that the unit cost of earthwork is UCEW, then the cost of construction per unit length will be EW by L, which that is a unit length earthwork per unit length times unit cost of earthwork. So, using this we can calculate what will be the total cost of construction also. So, with this we come to end of the graded bund. We also saw here that I mean how to consider various slopes, that is slope of the seepage line or the bed slope depending on the soil conditions, and if we know the total flow that we have to handle, how to calculate the H, and we also saw the derivation of a direct formula. Otherwise also it can be solved, but we saw a direct formula, and then we will apply all these concepts into next lecture to see how to really solve design problems on graded bund. Thank you very much.